Modern Way Educational Resources, and today I am doing a webinar using the Geometer Sketchpad and discussing the topic of geometry theorems and helping our students to actually make some meaning out of those. And so you'll see the opening title here. I'm actually doing this webinar in a little over a week from now, so this is kind of my practice run. And I'm going to be going through it basically just like I will on that day. If you want to come join me for the live event, there is a link to register here from the file. So before we get started, I just want to mention a couple of things in the notes section. And I'm not going to read all this to you. You're free to hit pause and read all the details if you want. The main thing I wanted to point out is that a lot of the wording for the theorems themselves I'm taking from a particular geometry book, actually a Key Press curriculum book called Discovering Geometry by Michael Serra. So I just wanted to point that out, that I'll be using that wording. So let's start by talking about some of those common theorems that we expect our students to be able to know and memorize and apply in the topic of special angles. So the top three that I picked for this are the linear pair conjecture, the vertical angles conjecture, and the parallel lines conjecture. Now you'll notice in this, at this stage, I'm using the term conjecture instead of theorem because we haven't proven it yet. And so right now, at this stage, it's just a conjecture, it's just a theory, just a hypothesis, and we're going to be using the Geometer Sketchpad, hopefully to prove these things and actually make them theorems. So you notice that I have here, in the traditional method, we often, the teacher will often just give these theorems to the students and say, here, memorize it, let's do some problems applying it, and then go on to the next topic. And of course we do this because in geometry there are lots and lots and lots of theorems. The problem, of course, is that often when we do it this way, the students don't remember what we've discussed in class, and so therefore when it comes time for the test or actually being able to solve a problem where they have to apply this, they just don't have it. And so what I'm going to demonstrate today are some ways that we could involve our students in actually exploring and coming to this knowledge on their own, creating it on their own, and having them take some more responsibility and ownership and participation. So how do we do that? Well, one way is that we could give them an activity in class. So if you'll notice, I've got a link here to a student activity guide that's going to take you to Dropbox, where I have a folder called Seeing Theorems, and I have several documents in here including the activity guides for some of the angle stuff, as well as some completed sketches along with the initial sketch that I'm using right now. I've already downloaded these, so I'm going to pull up Adobe, and this is our first angle exploration. So this is what we might give our students. So notice the way it's that it's presented here, and feel free again to hit pause so you can read this in detail, because I'm not going to stay on this screen for very long. But the essence is we have two girls in geometry class, and they're discussing the current topic, which is angles formed when two lines intersect. And so they both agree that there are four angles formed, but what they're disagreeing about are the relationships. So they know that the angles that are next to each other, so for example, this angle and this angle next to each other, adjacent angles, are defined as linear pairs. And the non-adjacent, so for example, the one that's got this R in it, and then this one across that's got the R in it, non-adjacent angles, are defined as vertical. But they're arguing over the relationship. So if you notice, Jane is saying that they're all congruent, and Mara is disagreeing, saying no, they're not. So Jane is trying to prove her case to Mara, and she's using a real-life example here of a railroad crossing sign. And she's saying, so see, there you go. And Mara says, I don't don't know if I think that's the case. Remember what Dr. Purdue always tells us. One example does not a proof make. And so that's kind of the setup, all right? That's the hook. And here is where we have given our students some direction. So you notice they have to construct all of the necessary components for their sketch in order to say what their thinking is on the relationship between these. So we're going to create the sketch the way our students would. So I'm going to start by grabbing the line tool and making a line. And then I'm going to make another line where they intersect, because that's the whole point, right? We're talking about the four angles formed when two lines intersect. So right now we're not talking about, for example, parallel lines, okay, ones that don't intersect in a plane. So we're going to talk about these four angles, so we need to have some measurements, and in order to do that, we have to be able to select the angles. So the first thing I'm going to do is construct the intersection. And then I'm going to use a new feature that is in version 5, which is this marker tool, which I think is like the most fantastic thing ever. It lets you click on a vertex and drag and create the angle mark. Okay, so I'm going to do that for all four of these. All right, and then I'm going to use these. Oops, don't want the line. Don't want the line. There we go. Took me a second, my eye-mouse coordination. And I'm going to measure these angles. Okay, so let me drag them over here so you can see them a little bit better. All right, so right away, your students might have a hypothesis, right, about what is the relationship between the vertical angles and the linear pair. Okay, so for one thing, they're going to notice that these two and these two, right, these two and these two, at least right now, are congruent. Now the wonderful thing about this software, unlike if we were just drawing this on the board and using a protractor to measure it, is that it's dynamic, which means if I drag any one of these points around, it changes the measurement, and the students can see that it's true not just for one case, right, which was Mara's argument, not just for an n of 1, but for all cases. Now you do want to be cognizant that if your students are doing this on their own and they're not already a little bit familiar with Sketchpad and sort of how it names angles, so for example angle ABE, right, this one right here, ABE, which is this one, is 28 degrees, that if they inadvertently drag to the point where the defining point for that angle, see how those go away if I drag it down here below the intersection? Okay, so you just want them to understand that this is a model, and so like a lot of models, there are limitations that you just need to be aware of. But so they can clearly see that vertical angles, meaning the non-adjacent angles that are across from each other, right, are congruent. Now then the question of what about the ones that are next to each other? Well, especially if they've managed to put the measurements like this, they might notice something. And you know, this is where you want to encourage them to do some experimenting. So what about, you know, when in doubt, add, subtract, multiply, and divide. So let's do that. Okay, so that sum is 180 degrees. Wonder if that's true for the other linear pair. And notice I'm just pulling up the calculator, I'm clicking on the angle measurements, and I'm doing that, of course, so it'll still be dynamic. So when I'm running around here with different numbers, the sum, notice, is still staying the same. So this is just a quick example of the kind of experimentation that we could ask our students to do. The finished sketch that we might expect from them for vertical angles and linear pair might be something where they've jazzed it up a little bit in order to show that the linear pair angles, the sum is 180 degrees, and the vertical angles, the measurements are the same, and so therefore the angles are congruent. Okay, so something like this. Now, if we talk about another way that we might get to this, so this first one, like I said, we did as kind of what about our students? How could we give them an example and get them to construct it? Another way that we could do it would be to give them a more open-ended exploration. Okay, so this link will take you again to Dropbox, where we were, right, with the theorems. And angle exploration 2 looks like this. Okay, so now we've moved on. So we've discovered this relationship between a particular group of angles, those formed by two lines that intersect, right? So in this diagram, the 1, 2, 3, and 4, they should be able to talk about, and the 5, 6, 7, and 8, they should be able to talk about. So they should be able to tell us right now, for example, that angles 1 and 3 are vertical angles, and therefore their measurements are equal. Same thing with 2 and 4, same thing with 5 and 7, same thing with 6 and 8. They should also be able to tell us that, for example, angle 1 and 2 form a linear pair, and therefore the sum of their angle measurements is equal to 180 degrees. But now we're going to kind of, as Emerald would say, we're going to kick it up a notch. Okay, so now we're going to talk about what about lines that don't intersect. Okay, so we know that parallel lines are defined as coplanar lines that never intersect. So clearly, if we're just talking about the parallel lines, which you notice in this sketch are the two black lines, they're marked parallel, right? They don't have any angles. They don't form any angles because they don't intersect. But what if we take a third line, this blue line, and what if we arrange it so it intersects both of the parallel lines? Then you notice we've got 8 angles. And we know that these all have names. Okay, here they all are listed. And this is where we say to the students, okay, we know what they are and we know how we're defining them. But what's the relationship? Okay, what's the relationship between them? So when I discuss this with my students, I start always with the definition, because that's really the key in geometry. That's what's telling us what's going on. So for example, alternate versus consecutive. I always start by letting them know that that term is referring to which side of the transversal. Okay, so for example, if I look at angle number 1, I can say that it is to the right of the transversal and above the parallel line. Okay, to the right of the transversal and above the parallel line. So to the right of blue, above black. If you go down here to our second parallel line and ask, and you can do this with your students, what's the corresponding angle? And by that I mean the one that matches the location to angle 1, which was to the right of the transversal and above the parallel line. Well, here's the transversal. To the right, that's 5 and 6. Above the parallel line, that's 5. So 1 and 5 are examples of corresponding angles. Okay? Another thing we can look at, if we look at the space between the two parallel lines, and we call that inside the parallel lines, right? We can see that angles 2, 3, 5, and 8 are all inside. That's where interior comes in. Okay, see here, interior. As opposed to 1 and 4 and 7 and 6 are all outside, right, of the parallel lines. They're exterior. So now we're ready to talk about something like alternate interior angles. Okay, so first, interior. That's 2, 3, 5, 8. Those are all interior. Now, alternate. One's on the opposite side of the transversal. So if I look at 2 and I'm trying to figure out what its partner is for the other parallel line. Okay, because we already know all the relationships with all of these lines, with all of these angles formed by the two lines that cross, right? 1 and 2 we know are vertical angles, 2 and 4 we know are vertical angles, etc., etc. Now we're talking about matching these 4 angles that are associated with the first parallel line with these 4 angles that are associated with the second parallel line. So if we look at angle 2, it's on the right of the transversal and it's inside. So we need an angle corresponding down here to that position except alternate. So alternate interior angles. So 2 and 8 because they're on opposite sides. As opposed to consecutive, which means on the same side. So consecutive interior would be 2 and 5 or 3 and 8. Consecutive exterior would be 4 and 7 or 1 and 6. Alternate exterior would be 1 and 7 or 6 and 4. So this is all stuff that you would have done in class, right? The definitions would already be in place. And then we would ask the students to explore these things on their own. So I'm going to do the same thing, choose the line tool, make a point, and construct a parallel line. And I'm also going to construct another point on that parallel line so that I can have some labels, right? I'm going to have a transversal, and I'm going to construct some intersections. Okay, and we would go from here using the same process. Let's say we're talking alternate interior angles, right? So we might label that one, and we may make it a particular color so it'll stand out, right? We can measure those and see that alternate interior angles, like these two, appear to be congruent. Okay, and so we would take that and continue. Scroll down so you can see. Okay, here's the finished conjecture. Notice that I've used some of the marker tools to be able to designate what matches with what and how. Right, so I used some examples. For example, consecutive interior angles, angle 2 and angle 5. And I'm using the hot text feature in version 5 so that when you roll over that, and of course, this is not necessarily, our students, their sketch may not look this fancy, but that's not really the point. The fact that they will have invested this time and this exploration in figuring this out, that's what is going to be the learning process for them. Okay, so these are a couple of examples of how we might teach these 3 theorems having to do with special angles. Now, what about special lines? So specifically for special lines, I'm talking about what about the slope relationships for our 2 special lines, parallel and perpendicular lines. How might we do that? Okay, so this way I'm going to say, okay, how might we do that if we just posed a simple question in class? For example, in algebra, we spent lots of time on slope. And we want to remember that slope is a measurement of a line, and it tells us 2 things, direction and steepness. We know that the sign tells us direction, so positive slope means it's going uphill, and by that I mean uphill because here in the United States we read from left to right, so this is going uphill. Okay, so a positive slope, uphill. Negative slope means, again, when we read from left to right, it's going downhill. Okay, so this is an example. Get rid of that because I don't need it right now. And we know that the value tells us how steep the line is in comparison to the identity line of y equals x, meaning a slope of 1. So if we know that a line has a slope, let's say, of 5, we know that it's very steep because 5 is bigger than 1, quite a bit bigger than 1. On the other hand, a slope of 1/3 is not very steep, okay, in comparison. But what about these special lines? What about lines that are parallel? Or what about lines that are perpendicular? You know, what about their slopes? And so the process, right, would be the same. We would be asking our students to start with this question, right? This would be the screen, the sketch that they would get, and to start trying to figure it out. Okay, what about lines that are parallel? Well, here's one line. I'll do what I did before. I'll construct another line that's parallel, and I will measure the slopes. Notice in Sketchpad, as soon as you measure a slope, it's going to put our Cartesian coordinate system on here, which is fine. Okay, so now I'm going to just do some experimenting. So the same. Wait, something weird happened right there. Ah, undefined, but undefined is still undefined, right? So the same. Even 0 and 0, still the same. Right? So you can easily see the relationship between slopes of lines that are parallel to each other. Well, the slopes are equal. Okay. And we could do the same thing with what about lines. I'll make this one a different color so we don't get confused. How about a nice purple? Okay. And I'll construct the perpendicular line. Okay, and this time measure the slopes. Them over here. Now this relationship is probably going to involve you giving them a little bit more guidance because they're going to see clearly it's not the same. And unless you give them some guiding questions, they may not see the relationship at all. Okay, and so remember what we talked about a second ago? When in doubt, add, subtract, multiply, or divide. Okay, so I'm going to skip ahead, and I'm going to multiply. Okay, and you can see that except for, notice there was one funky little place. I don't know if there we go. Except for the case where our lines are vertical and horizontal, right? Because 0 times undefined, it doesn't know what to do with that, right? So except for that, the product of the slopes is -1. Okay, so we would put some definition to that. We know that in algebra, if two products equal -1, another way of saying that is that they're negative reciprocals of each other. So we might end up with our conjecture written using that language. Okay, so, and again, we might jazz up some things. Notice we can put in the angle marker. These are all things that we can do with the new marker tool. Put in the parallel markings so the students can easily see that lines J and K are parallel. Okay, Oh, I wish I could talk to you right now so you can tell me how it's going. Okay, so that's special lines. What about polygon sums? What's another way that we could, so the two theorems that we usually talk about for this topic are the sum of the interior angles and the sum of the exterior angles for a polygon. And so, again, in the traditional way, we might just give them these two things, not as conjectures, but as theorems, and say, here you go, memorize it, and now answer a bunch of questions. You know, what's the sum of the interior angles of an octagon? And they have to fill in and kind of plug and chug, if you will. Okay, but what's another way to do it? Well, in this method, we could start with a cool kind of demonstration to have them see the answer. And you'll notice that I'm on purpose starting with, because I'm the teacher and I know, the easy case, okay? And I'm almost setting the stage to see if they will fall for it, right? So here's what I mean. We're asking the question, what is the sum of the exterior angles of a polygon? Okay, so here I have 1, 2, 3, 4, a pentagon, okay? And I'm going to shrink it to see what the sum of these angles, right? Did you get it? Undo it, right? So here are the exterior angles. The question is, what is the sum of these angles? Angles 1, 2, 3, 4, 5. Okay, what is the sum? Well, all of my students, and you too, can easily say, oh, well, the sum makes a circle, so therefore it's 360 degrees. Right? So we know at least for a pentagon, and by the way, don't be fooled, right? We can make it whatever size you want. Okay, shrink it, okay, as 360 degrees. Now, that's a pentagon, right? So that's 5-sided. What about if it's a quadrilateral? Okay, then what? Notice, still 360 degrees. And again, don't be fooled, right? Make it look different if you want. Shrink it and show them that, yep. Okay, so it's not, in other words, just because it looks like it's only one polygon, it's really not because of the dynamic nature of Sketchpad. Okay, so it's really zillions of polygons in here. Okay, so that was for a quadrilateral, right? So we so far know a pentagon and a quadrilateral. What about, oh, sorry, I already hit that button. What about a triangle? You probably have a guess, right? And of course, we would show other examples. Right here, we could construct a 6-sided, maybe a 7-sided, or we could give that to them for homework, right? And they would end up with the theorem as we know it, that the sum, I'll go back, the sum of the measures of a set of exterior angles is 360 degrees. Then we might go, okay, now, what about interior angles? And we could start by asking them, all right, so what do you think? Is it also going to be the same? And if so, what do you think the sum of that's going to be, the interior angles? And if it's not, then why? Now this #1 question is really important to have a little discussion time in class. Really get your students to think about it. Make a guess, right? Give an explanation. Don't just jump right ahead to what's the answer, right? Have them really think about it. Once they have a working hypothesis, then put them in front of Sketchpad and have them try to verify their conjecture. Okay, and notice I've given some tips here. Think about how you might utilize our previously used heuristics of ordered lists to help you. Because really what we want our students to do is employ several heuristics that hopefully we've modeled for them all along in class up to this point. For example, start with a smaller number. So rather than jumping ahead to what's the sum of the interior angles of a polygon with 30 sides, you know, start small. What about a triangle? And then go in order, right? Look for a pattern. So after you do triangle, do quadrilateral, do pentagon, do hexagon, make a table. See if you can figure out, is there a pattern going on? And then the goal is you want to be able to answer this question. The sum of the interior angles of a polygon within sides is. And we could do this with the polygon tool. Okay, so you'll notice that's what I'm using here. So there's a triangle. Here's a quadrilateral. And a pentagon. I'll just quit with those. So I'm going to use my same tool from before. I'm going to have my 3 interior angles and measure them. And use the calculator. Figure out what the sum is for this one case. Okay, so I have an answer for one, and then drag it around and make sure that my answer doesn't change. Okay, I may start a table where I record my information, okay, as I go. Does that make sense? And then, now remember, this is, you're not doing this, right, with the students. You have demonstrated these kinds of things all along. So now when you give them a question like this, they know, I can figure this out, right? So they're going through this process. And when they get done, it may look something like this, right? Where they have the sums and they figured out that, there's a key, right? There's a key to this, and that is convex. Convex, right? Because, let's look at the quadrilateral, for example. The sum is 360 degrees until it's no longer convex, okay? And then it is not equal to 360 degrees. All right. All right, does it make sense? All right, so that's polygon sums. So what about triangles? Well, as you know, there are a zillion triangle theorems. Okay, I'm just going to talk about 3. The sum of the measures of the interior angles is 180 degrees. Obviously, we just were talking about that in terms of polygons. This might be a theorem that you do before you get to the polygon sums theorem, so they can use it as a jumping off point. The triangle inequality conjecture, so this is a big one because it's used a lot in problems that show up on standardized tests. And then the side angle inequality conjecture. So how might we do those? Well, you'll notice I have the similar activity guide. I'll bring it up. In this case, go back to this for 1 second, I am using it in the context of an outside of class exploration. Okay, this is also something that they could be doing in a small group. It's something that you could have them do as a lab assignment outside of class, which is how I've used it a lot of times. And it looks like this. Remember, I was using this from the geometry, the Discovering Geometry textbook, so I do have some section numbers and references here. So obviously, if you're not using that text, you'd have to change these to match your textbook. But the idea is this. For each question, right, you're trying to find a general property, some truth that holds true for all of them. And second, you're going to use the findings to obtain correct answers to some sample questions. Okay, so here are some guidelines. okay, where here are the three questions, and I give them an idea about some of the wording, right? So if they have an idea of, oh, these are the things I'm supposed to be focusing on, I find that it really helps. So here are the questions. What's the sum of all the interior angles in a triangle? Does this sum ever change? And then the follow-on question is, what about if we add the next side, quadrilateral? Okay, another one. Can you make a triangle given any three lengths? And then the follow-on question or the extension, can you make a right triangle? So sample problems are given for each of these. And then finally, is there a relationship between the angles in a triangle and the opposite side? Okay. So, for example, let's say we're going to look at this one. Can you make a triangle given any three lengths for the sides? Well, for this, I really encourage you to use the idea of an initial sketch that you're going to give them. Okay, so I'll bring this one up and let you see it. So, for example, like this. Sorry, I know this is little. Let me make it a little bit bigger. Okay, so you would, because this, you know, you don't want, like any tool, right? You don't want the tool to get in the way of the learning. So rather than have them have to construct this and figure out how to do it, you want to give them the tools so that they can focus on the exploration. So in this case, here are the three sides, the red side, the blue side, and the green side, and the question is, can you make a triangle anytime? And of course, all it takes is one example like this, that you see no matter what you do, no matter how you adjust the angles or whatever, you can't actually connect the two B's to make this a triangle. And so they can figure out from this the rule, if you will, that we're trying to get to, which is it only works when the sum of two sides is greater than the length of the third side. Okay, so these are some examples. The finished sketch is listed here in Dropbox, the one called Triangle Completed. Okay, in case you're wondering, for the initial sketch, I just would copy that first page, the first page of that sketch, take the theorem off, and give it to the students as is. And actually, if you want me to, I can put that in the Dropbox as well. Okay, so finally, let me just quickly go over what might, oops, what's happening with my advanced button? There we go. What might an advanced theorems exploration look like? So, you know, once you've taught them how to do some of this stuff, it's really easy move to go to the advanced features. For example, how to create animation buttons, or show hide buttons, or how to actually get our sketch to prove things, at least visually. And that's what this one does. So this is actually the answer to the follow-on question of question number 2 about, okay, what about right triangles? So if we click demonstrate, you can see that we're taking the C squared side, right, and the A squared side, breaking them up into pieces and fitting them into the C squared side to visually prove the Pythagorean theorem. And of course, these, like it says here, are just a few of the ways that you can have your students explore theorems. There are so many others. I'll show you one. Again, in our folder, the one called Example Theorems. Again, I apologize that these are small. I made them on my laptop, okay? But the three that I have here are Blackwell's theorem, Napoleon's theorem, and the Steiner's chain of circles theorem. Okay, so these are all examples of advanced topics that you could have your students do. Well, I hope this webinar has helped you understand how you can make theorems so much more fun and help your students in seeing them, exploring with them, really thinking about these, and in a way that they're never going to be bored by these again. And also, they'll remember them. All right, thanks again.